Hi there, guys. We're about to do 1I. This is the binomial theorem, or the binomial expansion. That's what we're about to do. There's actually investigation 17 in front, which, as ever, I suggest that these are good things to do. Investigation 18 is a pretty decent thing to do as well. And then we get on to actually the binomial theorem in the book. So they state it, and I was just having a look at the formula booklet as well, and they give it in a bit of a different form in the book, so we'll just discuss that a bit. And yeah, there's another investigation here before we get on to the questions. Obviously, I'm going to focus on the questions, but the investigation's always pretty good. Okay, so the binomial distributions, get rid of myself. Okay, so I think if I was introducing this in class, I would just say to you, can you work out, to start off with, can you work out what is AB squared? You're walking into my classroom in the morning, I'd probably have this up on the board and say, just work out AB squared, AB all squared, that is. And I'm supposing that most people will know that one off by heart. And then could you work out AB cubed, and then A plus B, A plus B to the power of 4, and so on. And then I'd take it back a bit, and I'd say as well, what is A plus B to the power of 1? Because what we're looking for here are some patterns. And also, what is A plus B to the power of 0? So we want to see all of the patterns, and there are 2 extra examples which we can easily put in, which we know. Okay, well, A plus B is obviously, the power of 1 is obviously just A plus B. This one here, we've got A plus A squared plus 2AB plus B squared. And of course, this is just the expansion of 2 brackets. And when we do the expansion of 2 brackets, I mean, sorry to be obvious here, but we're doing everything in one times by everything in the other one and adding them all together. Some people like to write it down like a little Punnett square like this instead. Okay, well, obviously you've had loads of practice at doing that, but if we're multiplying together 5 sets of brackets, then you've got to think about all of the different combinations that you could have in order to do that. So, for example, you could have A times B times B times B, or you could have a different version that would give you that. You could have A times B times A times B times B. And there are many, many different routes through those brackets. Now, if you listened all the way to the end of the last video, you'll remember that that's a little bit like me saying A takes you to the right, so to the left, and B takes you to the right. And if you keep choosing left or right, you will ultimately develop the amount of routes that you need to get to positions in Pascal's triangle. Okay, so that's at the end of the last video if you want to go and have a look back at that. And that's why we're talking about this thing being analogous to Pascal's triangle and NCR. That all happened at the end of the last video. Okay, anyway, let's take that back. Oh, one other thing. I know I've been saying a few words lately which perhaps you might be less familiar with. Analogous, thought I'd just look up the definition to make this brief. They said Google comes up with this definition. It says analogous means comparable in certain respects, typical in a way which makes clearer the nature of things compared. So you often say that things are analogous. Here's their example. They saw the relationship between a ruler and his subjects as analogous to that of father and child. So they're comparing it to a situation which makes things kind of clear. Okay, and I've used the word arbitrary as well, though often I say arbitrary. So arbitrary is something we often say in maths as well. If we're just choosing something at random with no bias, we often say that that's an arbitrary choice. So their description of this on Google is just based on random choice or personal whim, rather than any reason or system. So it's a whim. Let's just choose this, for example. That's an arbitrary choice. Okay, let's go back to this. Okay, so anyway, you could work out this, you could work out this, and you can keep going, of course, A cubed, and you'll get 3 a squared b plus 3b squared a plus b cubed. Now, that would take you some time to work that one out because you'd need to do this times by this one times by another a times b. And that's going to give you 6 terms, 3 terms times by 2 terms. And then you have to condense those to simplify it to just the 4 terms underneath. Those are the 4 terms. Okay, and as you continue with this, you start to see patterns. You see that the highest power of a that you can get is 4, likewise with b. And then you get your numbers from Pascal's triangle. So we get 4 a cubed b to the power of 1 plus 6 a to the power of 2b squared plus, and maybe you can see how that one continues. It's going to go essentially backwards the other way. It's going to be the symmetry there, but with b being b cubed and a being just a, and then you're getting b to the power 4 at the end. But all of the coefficients which you're seeing here, so the 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. They're all coming from Pascal's triangle. And you should know Pascal's triangle, like all of the numbers within it, up until the fifth row, when n is 5. Perhaps that's the 6th row, in fact. So let me just get rid of some of this here, and let me do this one at the top. I'm going to do this in a second, just explain that again. So just another little thing here, put down just at the start that we're talking about the binomial theorem. But when we talk about the binomial theorem, it's the same thing really as talking about the binomial expansion. We're talking about the expansion of brackets, and it's called binomial because there's 2 things inside the brackets. So if we were talking trinomial, we'd have 3 things inside the brackets to the power of n. So here we've got 2 things inside the brackets, and those brackets, that set of brackets raised to a particular power. Now, this is different to the binomial distribution. So later on, you deal with the binomial distribution, and that's talking about probability. So we're definitely not dealing with that at the moment, but these 2 things are basically the same. Binomial theorem or the expansion of a set of binomial brackets are the same thing. Okay, so I'm about to do this one here just to make it kind of clear. And so we're going to deal with a plus b to the power of 5. In this case, I'm going to write this thing down. So fully expanded. I'm going to show you the general form for this one. So for this, again, we're going to put Pascal's triangle just down to the side here. 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, and 1. And hopefully, if you saw the last video, you can see that each number that you get after you've made this start is the sum of the 2 numbers above. Okay, and these things are the same as using NCR. So, for example, you're getting 5, choose 0 here, and 5, choose 1 here, 5, choose 2, 5, choose 3, 5, choose 4. This is 5, choose 5. And this row would be full of 4, choose 0, 4, choose 1, and so on. Okay, and remember, for example, 5, choose 2 could be also written as 5, 2 in these brackets, looking a bit like a vector. So often it's written down like that instead. On your calculators, if you've got one of the old style calculators, when you type it in, it might look like that when you type in this combinations symbol. Okay, so now why is this the same as this? We kind of discussed that last time round, but say for example you wanted to get the term out which is, I don't know, a squared b cubed. Okay, now that's basically saying let's get 2 a's and 3 b's. Now this is what we started the previous video off with, and there's lots of ways of doing this between the brackets. You've got a, b, 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 but you've got many ways of doing that through here. You've got you could do a, b, a, B, B. And there are many combinations here, and you're choosing either A or B from each of those brackets. Now, how many different words are there essentially? So for example, the second one, which I created here, would be A, B, A, B, B. Okay, so that's a different word, and that's a different way of getting through the brackets. So asking how many different words that you can make with this, if you remember, was the same as saying 5 factorial, but A and B can be either way around. And there are 6 ways of arranging the 3 B's, okay, the 3 different B's, which is what we dealt with last time round. So we're going to need to divide by 3 factorial as well. Now that's your 5 choose 2, or equivalently, that's the same as 5 choose 3. Okay, so it's all about bouncing between the brackets, essentially. So if we want to know how many ways there are of doing this, we need to choose 5 choose 2 or 5 choose 3. It's the same. Okay, so we get 10. There are 10 ways of getting this. So we put a 10 here in front of this, and that's one of our terms in the middle of the expansion here. Okay, now you can do that for each of your terms, but of course, they're just going to give you these numbers here. So there is only one way of getting a to the power of 5. It's just this. There's no other way of getting a to the power of 5 when you're timesing the 5 brackets together. Likewise, that's the same for b to the power of 5. In terms of a to the power of 4, b to the power of 1, well, we could have the b in any one of 5 positions there. So the b could be in this position, this position, this position, but the others have to be filled up with a's. So there are 5 ways of doing this, and that's just taking the 5 off here. Now, we've already explained the next one, so I'll go through that again. A to the 3b squared plus 5 lots of sorry, not 5, got 10 next still. 10 lots of a squared b cubed. Just going through all of the different combinations I can get with my powers. Got plus 5 lots of a b to the 4, and then plus, just on the end, b to the 5. Now, you could really write this in a different way. Now, for the first, maybe let's just take this one, okay? So for this one here, you could say that that's 5 choose 1, and that's a to the power of 5 minus 1, and that's b to the power of 1. Okay, now the first term you could write in a similar sort of format. You could say, well, that's 5 choose 0, a to the power of 5 minus 0, and b to the power of 0, because b to the power of 0 is 1, so it's going to disappear. Okay, so what I'm building up to here is the general format. So the general format, we carry on, we can keep doing that, of course. So the general format is going to be NCR, and then we'll put in a to the power of n minus r. Okay, originally we took away 0, we're taking away 1, next one we'll take away 2. Then we have b to the power of b to the power of 0, 1, and those powers increase. So this is b to the power of r. So if you want a general term here for the expansion, there it is. That's how you get any particular term out from your expansion of an a plus b to the power of something. Okay, well, we could go a little further here and say that our full formula is, in fact, the summation of all of these things, because we're adding all of these things together. So our full formula, our full binomial expansion, will be choosing r to go from 0, because we started off with 0, all the way up to n. And that's going to give us n plus 1 terms. So, for example, on the 5th row, we have 6 terms. Okay, I call that the 5th row. The book calls it the 5th row as well, but strictly it's the 6th row, isn't it? Because that's your first row. The row with 5 in. And of course, you can see that you get 6 terms out here from the expansion of 5 brackets. So we're getting n plus 1 terms from 0 up to n. So this thing, pretty neatly there, we've just come up with the binomial theorem. That's the expansion of a set of brackets where you've got two things inside the brackets to the power of n. Right, and that's going to give you not only every single term in the middle, that's going to give you your summation of all of your terms as well. Okay, right, well, we're ready to start the questions then. Oh, let's just have a look briefly at how the book writes this, and let's have a look at how the formula book writes this as well. So in the Oxford book, zoom in on this one. So you can see they say a plus x to the power of n there, whereas I've chosen a plus b, and I chose a plus b to be the same as the start of the last exercise, essentially, when we talked about a, b, b, b. Okay, and they've come up with exactly the same formula at the end. And what else do they put? They put some conditions on the top. They say n belongs to your positive integers. Okay. And they say a and x belong to your real numbers. So it doesn't matter about a and x being natural numbers or integers necessarily. Okay, well, let's have a look at the formula booklet then. What do they do? Well, in the formula booklet, it's kind of partway between what I did and what the Oxford book did. So the formula says a plus b, not a plus x, but then it gives the terms in the middle, and in particular this one in the middle, this thing here. Let's reduce that down. Just this thing in the middle here, the n c r a to the n minus r b to the r. They've got that particular middle term as well. Oh, and they've also got the expansion of NCR just to help out there. You should be really familiar with that. But they haven't got the first term given as n choose 0. So they haven't used the sort of general form for the first and the last term there, which is fair enough, to be honest. That's kind of overcomplicating things. So that's what's given in the book. That's what's given in the formula booklet, and that was what was given in the book. Okay, well, let's go down. Let's take this. Let's just zoom out a little bit. A bit too big. Okay, let's take some of these questions. This is example 48. And you kind of chuck straight in the deep end here, because they don't just simply say expand this. They say find the values of A, B, and C. So yeah, they're taking no prisoners here. Okay, you're going to really have to show your worth straight away. So the expansion of this one, now I think I might just try and expand this one anyway. So let's have a little look. We're getting, and I'm just going to put it all up here, run out of space if I type too much. So I'm going to do 1 to the 5. And now I would kind of lay this out on your page, starting pretty small and realizing I've got 6 terms to fit in here somewhere or other. And I would just put in all of my 1 to the power of 5, so 1 to the 4, 1 to the 3, 1 squared. I mean, I know they're all 1s, okay, but I'm just showing you this time round. And I've probably done them all way too big. So 1 to the 1 and then 1 to the 0. And then we've got the other bit. So remember, we have the form of a plus b. So b here must be minus 2x. Okay, so I'm going to put in minus 2x to 0, minus 2x to the 1, minus 2x squared. Trying to write smaller so it all looks a bit weird. Minus 2x to the 4, and minus 2x to the 5. Okay, now I need my coefficients from Pascal's triangle again. And so I'm going to put in front of these, tell you what, let's choose, put coefficients in with a different color. So the coefficients are 1 and 5. So there's a little times there. 10, 10, 5, and 1 at the end. Now they're also all filled with plus, because that minus has already been dealt with the minus inside the brackets there. Okay, so that's what we've got. Sorry for making the massive 1s. They are 1s. That's a 1, okay? Okay, so when we multiply this out, that's to the 0, not to the power of 6. So that's going to disappear essentially, and we're just going to get 1 in this case. In the next one, well, all of the ones just become 1. 1 to the power 4, 1 to the power 3. So we're going to get, take that back, we're going to get one lot of this thing here times by 5 minus 10x. Then we've got minus 2 squared. So that's going to give us 4x squared, but then times by the 10 gives us plus 40x squared. And then in the next one, we've got this thing. So cubing minus 2 gives us minus 8. Then times by the 10 at the front, we've got minus 80x cubed. And on the next one, we've got 16 times by 5. 16 times 5 is also 80. We're going plus 80x to the 4. And on the last one, we've got minus 2 to the power of 5 is minus 32. And then x to the power of 5 on that one as well. So that's the full expansion. Okay, so in fact, we didn't really need all of that. We only needed these terms here. So these terms in the middle were the ones which we needed. So we actually need to answer the question. We've got A. Change my pen and just put this one back into charge. Okay. And yeah, so we only really needed to those 3 terms there. We also needed to state what A, B, and C are at the end. So A is minus 10, B is 40, and C is minus 80. Okay, right, good. So let's get rid of all of that. And then for part B, so we've got something similar going on here. You can see A is at the top here. Because there's 9 terms and it goes up to the power of 8, this means that our maximum power here needs to be 8 as well. So you can see 5 and 5, so it's going up to 8. So A is 8, that's pretty easy, and then we just need those 2 first terms. Now in this case, I'm just going to use the formula. So the formula is NCR for any particular term, and we have A to the power of N minus R, and then B to the power of R. So for this term here, we're going to have 8 choose 1 times by 1 to the power of 8 minus 1 times by x over 3 to the power of r, and r in this case is going to be 1. Okay, so that's going to give you your first term, and the second term, similarly, it's going to be 8 choose 2 times, now this is, I'm not going to bother writing that because that's just 1, of course, and then we'll get x cubed to the power of 2. Okay, so, well, you can either take on your Pascal's triangle if you know your line 5, 1, 5, 10, 10, 5, 1. You can create your next couple of lines, 15, 20, and let's try 7, 21, 35, and 1, 8, 28. And I don't think we need the next one, actually. We only need this and this. So there we go. We've got 8 choose 1 and we've got 8 choose 2 there, just from extending Pascal's triangle. Okay, well, you can multiply those ones out and simplify them. Let's just do this. Okay, this one is 28 times by x squared over 9. So you should have 28 over 9 as your answer for C. Let's just check that one out, see if I got that right. There we go, 28 over 9 for that one. And you can see the working out in the book there as well, if you want to pause on that page and see how they've done it. You can do. I seem to have found a sort of slightly quicker way of doing it. Okay, so with C, okay, so for part C, again, we're looking for A, B, and C. And here it's a little harder because you've got A tied up here. And well, we can see that B is going to be 2 to the power of 7. I think that's pretty straightforward. So again, your first term is going to be 7 choose 1. And then we've got 2 to the power of 7 minus 1. Sorry, I'm wrong there, aren't I? first term is going to be 7, choose 0. We're going to have 2 to the power of 7 and ax to the power of 0. That's the first term. And then for the next one, we're going to have 7, choose 1, 2 to the power of 6, so 7 minus 1 there, and ax to the 1. And that's going to be equal to 2 to 4. So that will enable us now to work out what a is. And then for the last one, we've got 7, choose 2 times by 2 to the 5. And then we've got ax squared there. And that's going to give you your answer to C. So I'm not going to labor this one too much. You can obviously expand this one here. Yeah, so you can expand this one here. I kind of messed up a little bit there. I wonder if you can see what I've done. So on this side, I've just come up with a coefficient, but on this side, the coefficient of x. But on this side, I've actually left x in. So really, I should have my x there, but the x is going to cancel on both sides because it's not 0. We're allowed to do that. So yeah, okay. So this is obviously going to become 1. Step there as well, haven't I? So this is going to become 1 at the top, and then 7 choose 0 is 1 as well. So b is just 2 to the power of 7, and then of course this is 7. 2 to the 6 is 64, and so we've got 7 times 64 times a equals 2 to 4, and I've cancelled the x, and then you can solve that equation. And then for the last one, 7 choose 2. I've forgotten what that is now. 21, I think. 21 times 32 times a squared times x squared, but let's cancel the x squared off both sides because it's not 0. We're allowed to do that, and that's equal to your C as well. Now you'll obviously need to put your a from there into this one. Okay, sorry if I don't do the actual calculations, but we can check the book. So you should get answers of a is equal to 1/2, b is equal to 108, and c is equal to 168 there. Okay, right, example 49. So let's do this one. So it says find the coefficient of x cubed, y cubed in this expansion. Okay, well actually that seems to be a simpler question from my point of view, because we still just can use this NCR, a to the power of n minus r, and b to the power of r. This is the thing that you need to remember. We're using it every single time in every single question. Either we're using it in every term, or we're using it for the particular term that they care about. So you should know what coefficient means. Coefficient means the number in front of this term. So in order to get x cubed, y cubed here, you can see that we're going to need to have x cubed and 3y cubed is going to deliver us that term. So that's the term in the middle when we've got equating it to this thing up here. Now, hopefully you should all see this fairly quickly, that we've got 6 terms, n is 6, and in order to get x cubed, we'll need to have a 3 there for r, because that's going to give us n minus r being equal to 3, but also we need a 3 there as well. So, okay, so that's the term that we need. We've got 6 choose 3 is 20. We've got x cubed and times, my dot for my times, so 27 y cubed. And then, of course, you can simplify that one. So 20 times by 27. That's an easy question, in fact. Okay, let's have a look. Yes, that's the same as that. So example 50. See how many there are. Oh, need 2 more questions here. Example 50. Use the binomial theorem to expand 2x plus 3y all to the power of 5. Hence, find the value of 2.03 to the power of 5, correct to 5 decimal places. So the second part of this question is going to require some creativity. to look at this and see how it relates to this. But first part of the question should be straightforward. Now I'll do this one quickly and just write it down, giving myself as much space as possible. So I've got 2x to the 5, 2x to the 4, 2x cubed, 2x squared, 2x, and I always run out of space at the end, can't help it. And then there's 2x to the 1, and then there's 2x to the 0 after that. So we've got 3y to the 5, 3y to the 4, 3y cubed, 3y squared, and we've got 3y there, and there's no 3y there, so I give way too much space at the front. Now I'm going to put my Pascal's triangle numbers in. Of course, we've got 1 here, so I'm not going to bother putting that in. And then we've got 5, and then 10, and then 10, and then 5, and then 1 again. Of course, we'll just fill this up with pluses, plus there, and plus at the end. Okay, so the expansion is just expanding all of those terms. So we've got 32x squared, and what's this? This is 16 times 15. Sorry about this. Yeah, 240. Should have known that by x to the power 4y. And then 9 times a, so 72 plus times 10, so 720 x cubed y squared. And then what do we got here? We got 9 times 4 times 10, so 320. No, 360. 360 x squared y cubed. And then 3 to the 4 is 81. That's the same as 9 squared. Times by 10 gives us 810. 8xy to the 4, and then 3 to the power of 5. So it's 81. What have we got? 3 to the power of 5. I can do this in my head, really. Okay, so should be doing that in my head. 243 to the power of y to the power of 5. Okay, yeah, sure. That's 81 to the 3. I was panicking there. Hey? Right, so 81 times 3. Right. Okay, so there's our expansion. Hopefully that's right. Let's just check it out. 32, 240, 720, 1080, 810, and 243. Oh, what did I do wrong there? So with this, what did I do? I did times by 9, didn't I? There's another times by 3 there. Okay, sorry about that. That's 1080. Oops. Okay, so always good to check with the book. You can't do that in the exam, of course, but you can use your calculator. Okay, usually. Right. But not in all exams, to be honest, but right. Okay, so there we go. There's that. And it says, hence find the value of 2.03 to the power 5, correct to 5 decimal places. Okay, so you should basically equate this to this. And this is like trying to look at two things and say, well, okay, well, how are they the same? Now, this is an equation with 2 unknowns and 1 equation. So we can't solve for x and y, but we can come up with clever values for x and y. Clever, nice, easy values. So although there's multiple choices of how to make this work, you can probably see that if I do 2 times 1 there and 3 times 0.01, I get my answer of 2.03. Now, these things are really easy to put in here, right? So when we put in x is equal to 1, all of those x terms are going to disappear. And when we put in y is equal to 0.01, well, that's really easy to calculate. When I do 0.01 squared, I get 0.0001. Okay, or if you want to change them into fractions, you can do if you find that easier to work with. Yeah, okay. I mean, a little tip on this, by the way, if you're timesing something, hang on, you're saying 0.02 times 0.03, if you trust my numeracy skills here, if you times these two things, you've got 1, 2, 1, 2 spaces there. Hang on, 1, 2, and 1, 2 spaces there. Then when you times them together, you'll get 1, 2, 3, 4. I mean, that's just a little tip, right? 1, 2, 3, 4 spaces it will go back to. So hundredths times hundredths gives you thousands. And if you end up with a 0 there, if this was a times by a 5, then of course that's going to give you a 1 and a 0 on the end. So, you just need to be aware of some of these little tricks. And hopefully you've got strong numeracy skills anyway. Okay, so what are we talking about? Talking about substituting in 1 for x and into this or into the thing or into this thing here, we're talking about substituting in 0.01. And then you can calculate this thing to 5 decimal places. Right, to spare you the chat, that's exactly what's happened here. And you can see that 2 to the power of 5 gives you the 32 at the front. But as soon as you're putting in 0.01 to the power of 5, you're getting an extremely small number at the end there. And in fact, a number which is irrelevant in terms of the question, because we only need to get this thing to 5 decimal places. So the last term is actually not important at all. Okay. Right, and obviously you're going to add all those things together and you can use your calculator to do this. Now, later on, this technique is going to be pretty important to make approximations to calculations without using a calculator. So skills like this were really useful ways of working out difficult calculations. I mean, trying to do 2.03 to the power of 5 is going to take you a long time in terms of calculations. But since you know how to do 0.01 to the power of 5 really quickly, then this becomes a much more efficient method to work out 2.03 to the power of 5 rather than doing 5 or 4 multiplication sums. Yeah, so this you can see could be used as an algorithm. A calculator could be using this algorithm to work out this calculation as well. Okay, so we've got one more question left. And example 51. So let's take this one here, example 51. Find the term independent of x in this expansion. Okay, so when they talk about the term independent of x, they mean what's the coefficient of x to the power of 0? In other words, which term doesn't include x? Okay, now from my point of view, if I was looking at this question, I would just be thinking, I don't have many combinations to consider here. And I can see it's not going to be the first combination. I can see I'm going to get to start off with x to the power of 12. And I do my, anyway, let's just write this down. NCR, a to the power of n minus r and b to the power of r. So I can see if my first term is going to be x squared to the power of 6, and I'm clearly not going to get x to the power of 0 there. So probably I'm not going to get it with the next one either. So I'm just going to flick on. I think I'm going to say, let's try x squared. Okay, so let's try the one where I've got x squared, and then I've got minus 1 over 2 to the x to the power of 4. Oh, and I can see I've got it already. So I've just done a little trial and improvement in this. I've seen here I've got x to the power of 4, but here I'm going to get out x to the power of 4 on my denominator. So the two things are going to cancel. So, I mean, I could try other numbers, of course. I mean, if I tried a 3 there, I'm going to get x to the power of 6 out here and x cubed on the bottom. So clearly x to the 6 will cancel with x to the x cubed, but leave us with x cubed. So that's not going to work. So there's not many combinations that you need to go through here, and I would probably just do it like that. And so this is going to be your term. And then you're going to have NCR as well. So you're going to need to put in 6, either choose 2 or choose 4, doesn't matter, because probably let's be consistent with this thing up at the top. And then let's put a 4 there, and that's going to be your term. Okay, so if we work this one out, we've got 15, so 6 choose 4 is 15. We've got x to the 4 there, and then we've got the minus is going to disappear because we've got an even power. And so we've got times by 1 over 2 to the 4 is 16. Also, we have x to the 4 on the bottom. They're going to cancel, so our answer should be 15 over 16. Check that out. Phew, I got that one right. Okay, right, but the book does it slightly differently here. Okay, so now I'm going to have a go at the way in which the book does this question. And so this is a little bit more complicated. So again, I'm going to set up NCR. So our general term, we've got a to the power of n minus r and b to the power of r. So we're using this one here. I'm going to use that with this to try and figure out where is my x to the power of 0. Okay, so we've got 6, so a little bit more space. 6, choose r, and then we have x squared to the power of 6 minus r. And then we have, well, let's split this into 2. So we've really got minus 1. Let's keep it as 1 just for the moment. We have this to the power of r. Okay, and we're going to need to play around with this a little bit to get the x on the top there. So we could maybe split this one up. Let's just take all of this kind of stuff out to the front. So I'm going to split this up into 2 things. I'll split it up into minus a half and also 1 over x there. And I'm going to bring the minus the half to the power of r to the front. And I'm going to do the 1 over x as x to the minus 1 to the power of r. So to bring that minus a half to the power of r to the front, and I've still got x squared to the power of 6 minus r, which I could simplify to. Times those 2 powers together, I'll get 12 minus 2r. And then I have x to the minus 1 to the power of r. Or in other words, saving a little space here, x to the power of minus r. Okay, now that's not easy, and you probably want to use a couple more steps there to get to that answer to make sure that that's right. And then essentially we can ignore all of this because we're not interested in currently the term, but we're not interested in the answer or the coefficient essentially, which is what the question is asking us. We're just interested in when is this going to be equal to x to the 0 at the moment. So let's combine this. We've got x to the 12 minus 3r now. When, remember, laws of indices, we've got the same base number. We can add those 2 powers. And we basically want to say, well, when is this equal to 0? So again, let's write it out fully. Minus a half to the power of r times this thing. Okay, now I need to do a little working out separately. I've got 12 minus 3r is equal to 0. And I can see that if I solve this, I get 12 to the power is equal to 3r. So r is equal to 4. Now, what does that mean? That means that we need the power of 4 on this, but we need the power of 2 on this. Remember that r is the power on the second term, not on the first term. So that's the same as what we were getting before. We're saying square this and do this to the power of 4. Now, this method here is much harder. But if they talked about this to the power of 52 or something or other, then you're not necessarily going to be able to go through your combinations easily. So, so this is a good method by basically, again, taking this general term in the middle of your binomial expansion and working with this in order to work out what r is, because we know that the power on x, going through some laws of indices there and some algebraic work, the power of x needs to be 0. So then we solve this thing over here. So there we go, working out a side that we're doing, and then we can see r is equal to 4. We can substitute that in there, and we'll end up getting our final answer just as before. Check how they do that in the book. Yeah, they've done it in the book as well. So similar process there. I think there's not many lines of working out there, and I think you could be scratching your head for a while figuring out how to get from their first line at the top there to the equals bit. Yeah, and I think that's relatively tricky. Either way, from my point of view, because the numbers are so low here, I would just do this by trial and error. I would say try 2. 2 seems reasonable. X squared to the power of 2. X squared to the power of 2 gives us x to the 4, and that gives us 4 on this. So the 4 on the denominator will cancel with the x to the 4 bar. Okay, right, guys. Well, thanks for listening in. Let's just see what's coming up next. We have 9 questions there. So again, worth doing all of these. There's a lot of work going in before you get to those. Some people, of course, will have seen these before and will have seen the binomial expansion before. So some people know how to do that. So this will be a recap. If you're in a position where you're doing this for the first time, you definitely need to go through all of those questions. And for the next part and the last part in this chapter, we're talking about 2 extensions to this. The binomial expansion when we're talking about using negative powers, coming up with an infinite series there, and the binomial expansion when we're using rational powers, so fractions as powers, and again we're getting an infinite series there as well. So that's the last little bit in this chapter for myself, really, and there's a couple of questions there to go through. Okay, guys, well, thanks for listening. Well done on your efforts, and I'll see you later.